This video is part 2 of the lesson on proving trig equations. We're going to dive right into the next 10 examples of these proofs, and each one will show a different approach or technique for proving these things. Number 9 is one of the few thus far that I'm actually going to work on the right side, and that's because we have secant plus tangent, and so I'm going to work at adding these together. If I look at the left side, there's not really much to do. We just have a fraction, and there's nothing to break up in the numerator, so we're kind of stuck. But on the right side, I know secant is 1 over cosine, and tangent is sine over cosine. So that works out really well because they already have the same denominator. So now I'll add those together. Now we have 1 plus sine over cosine. Now, I normally don't write both sides of the proof, I just work on one side, but in this case I am actually going to write cosine of theta over 1 minus sine, because I think this is really interesting looking at kind of the symmetry of this proof. Of course, we're not done yet, but the sides look so similar that it almost seems confusing as to where we should go because they look so similar already. Now remember, I can technically only work on the right side, so I have to do something over here to try to change it into this. This is actually one of my favorite techniques just because it's so simple. And the idea is, if you look at the right side, we have cosine in the denominator, and what we're trying to get is a 1 minus sine in the denominator. So if you have no other way of figuring out how to make that happen, just put 1 minus sine in the denominator. But of course, you can't just put it in the denominator fraction, you got to put it on the top too. So 1 minus sine. So basically, I'm multiplying the top and the bottom by the same thing. And careful with all these parentheses in the top because we do have to FOIL that together. In other words, I have to multiply all of this 1 plus sine. I can't just distribute the sine through. But the good news is the two factors in this numerator are conjugates, so when you multiply them together, you'll get 1 minus sine squared. On bottom, I'm just going to leave these factored apart, so cosine of theta times 1 minus sine of theta. Now that got us closer in two ways actually, because now I have a 1 minus sine in the denominator, which I want, and also the numerator is 1 minus sine squared, and I know that's cosine squared. And in the final answer, I know I want a cosine in the numerator, so that's getting me closer as well. So now I'll just cancel this cosine out of the denominator with one of these on top, and we've finished our proof. In number 10, we have cotangent squared over 1 plus cosecant equals 1 minus sine over sine. Now I'm going to choose to work on the right side, and that might be kind of strange because the left side seems a little bit more complicated since we do have something squared on top. But this is an example of that guideline from last time that just said, like, just try something. And when I look at this problem, the first thing that I think of trying is taking this fraction and breaking it up, because we have two things in the numerator over sine. So since that just seems like the most obvious step to me, I'm going to try that and see where that leads me. If you see a different way of doing it, you should try that. So on the right side, I'll break this fraction up. We'll have 1 over sine of theta minus, and then sine of theta over itself. So 1 over sine of theta is cosecant of theta. And then sine over sine is, of course, just 1. And honestly, at this point, it might seem like we're kind of stuck because we have two terms on the right, neither of them is a fraction, and we're supposed to get to this. One trick I've found that has come to the rescue a bunch for me is to multiply by the conjugate. So we have cosecant minus 1. I'm going to multiply by cosecant plus 1. But I can't just multiply the right side by cosecant plus 1. Like, that would completely change that right side. So here's the other part of the trick. I'm going to put this over cosecant plus 1. So now really what I'm doing is just multiplying the right side of this equation by a weird looking way of writing 1. And multiplying by 1 is totally fine. So here's what that does for me. It gives me a fraction, first of all. It puts cosecant of theta plus 1 on the bottom, which is nice because I wanted 1 plus cosecant, so I'm set. And then on top, we have these conjugates, cosecant minus 1 and cosecant plus 1. When you multiply those together, you'll get cosecant squared minus 1. Which is perfect because that is cotangent squared, and that's what we want. Moving on to number 11, this is a great factoring example, and we haven't seen a whole lot of this. But if you look at the right side, we have two terms, tangent squared times secant squared minus tangent squared. And they both have that common factor of tangent squared. So I'm going to factor that out, which would leave me with secant squared minus 1. So I'm going to leave the tangent squared alone. And of course, that's because we're trying to get to tangent to the fourth. So I want to make sure I have a bunch of tangents. I just need to change these into some more. And secant squared minus 1 is another tangent squared. So tangent squared times itself is tangent to the fourth. So that one was pretty quick. Number 12, we have sine to the third times cosine to the fourth equals cosine of the fourth minus cosine of the sixth times sine. So the first thing I notice is that I want to make sure I have 4 cosines on the left, and I've got a whole bunch of them on the right. But in both of these two terms, they both have at least cosine to the fourth. So again, I'm going to factor cosine to the fourth out of both of those terms. So cosine to the fourth of x, and then in this term we would just have 1 left over. In this term we would have minus cosine squared, and then the sine is just kind of staying at the end here. All right, now 1 minus cosine squared, if you look at your Pythagorean identities, that is sine squared. So now we have cosine to the fourth of x times sine squared times sine. And if you put those signs together, we've got cosine to the fourth of x times sine to the third. And that's it. Number 13 gives us the square root of, and then 1 plus sine of x over 1 minus sine of x, that's all on the left, and then 1 plus sine of x over the absolute value of cosine of x. The left side of this problem is obviously more complicated, having the square root in there, so I'm going to try working on that side. Now, I obviously want to get rid of that square root in order to match it up with the right side, but I can't just square that side, because if you have an equation, if you square the left side, in order to keep it an equation, you'd have to square the right side, and I can only work on one side. So squaring something is totally out of the question. So we have to be kind of creative and think of a different way that we can make something be squared. So what I'm going to do is just first of all, just write this big square root. We have 1 plus sine of x on top and 1 minus sine of x on bottom. But what I'm going to do is I'm going to take this fraction and multiply inside the square root, inside this fraction, another 1 plus sine of x on top and bottom. So that keeps the fraction equal. That's basically multiplying by 1, so it's okay to do that. And the great thing about this approach is we have 1 plus sine of x squared. It's times itself. So I am going to write that out in the next step. We have 1 plus sine of x. I'm going to keep that in parentheses, and that factor is being squared. And then it's over, and I can simplify this too. Again, we have those conjugates, 1 minus sine times 1 plus sine. So that would make 1 minus sine squared of x, which is great because that is cosine squared. Now, before I go too much further, I do actually want to take a step back and point out the difference between these two things. Right on top, we have 1 plus sine of x. That factor is being squared. On bottom, we have sine of x being squared. So those are different things. But anyways, back to this step, we have the square root of this fraction, and now on top and bottom, both of those things are being squared, so we can just cancel out the square root with both of those squares. You got to do both the top and the bottom. And that leaves us with a 1 plus sine of x on top and a cosine on bottom. Now, you might be wondering, where do the absolute value bars come from in this side of the equation? And it's just kind of a minor detail, but basically it's because right here we had cosine squared, and cosine squared, since it's being squared, it will only ever spit out positive values. And then you take those values and you take the square root of them, that will also just spit out positive values. So at this point in the problem, this expression was only spitting out positive values. But now we get down to the simplified expression. We have 1 plus sine over cosine. If you think of the sine value, like the sine graph oscillates between positive and negative 1, so that will be between positive and negative 1, but if you add 1 to it, that will always be at least 0 or positive. Okay, but on the bottom, cosine, again, oscillates between positive and negative 1, so that could spit out negative values. So these things technically aren't the same thing yet. To fix it, we need to make this only spit out positive values, and that's why we put the absolute value bars around the cosine of x. So that finishes out our proof. In number 14, we have the natural log of the absolute value of the tangent of theta, and then natural log of sine of theta minus natural log of cosine of theta. And we have all these absolute value bars, so it looks like kind of a mess, but it's not too bad. You do have to remember a little bit about your log properties. So remember, if you're subtracting two log terms, you can change that into one big fraction, one log term. So sine of theta over cosine of theta. These absolute value bars are kind of obnoxious, but the only reason for that is, again, sine and cosine can both spit out positive and negative values, but you can only evaluate natural logs of positive numbers. So that's the reason for all the absolute value bars. They're just kind of a detail that we have to deal with. And we're almost there. Now we have natural log of, and sine over cosine is tangent. So this problem was pretty quick too. It was just a reminder of natural log properties and why we have to use these absolute value bars. In number 15, we're finally going to use a sum or difference identity. In this case, we have sine of 3 pi minus x, so I'm going to use a difference identity. Remember, they're written usually as like sine of u minus v, but that formula was basically sine of the first, so sine of 3 pi, times cosine of the second, so cosine of x, and then minus cosine of the first thing, so cosine of 3 pi, times sine of the second angle, so sine of x. And then, so obviously I'm working on the left side, I'm just going to leave the right side alone. And now somehow we have to simplify this expression down to just sine of x. Well, let's look at sine of 3 pi. If you think about on the unit circle, 3 pi would be, well, here's 0, and then 1 pi, and then 2 pi, and then 3 pi. So 3 pi is over here on the left, and that's the point negative 1 comma 0. Well, the sine value, or the y value, is 0. So this is like 0 times cosine of x, and that term's just going to go away. But let's keep writing here. So then we have cosine of 3 pi. Well, cosine is the x value, that would be -1. So -1 times sine of x. And this -1 is different from the negative outside there. So now I can cross out the 0 times cosine of x. The negative times -1 becomes positive, and we just have sine of x. So sine of x equals sine of x. So sometimes in these proofs, you will actually have to evaluate these little trig expressions. Number 16 has kind of a complicated left side. We have sine of x plus y plus sine of x minus y. So we have both of these expressions where we can use those sum or difference identities. So as you're writing this, just be really careful with your x's and y's that you're writing. But now look at what we have. Again, you kind of have to read this carefully, but we have sine of x cosine of y. Now this is cosine of x sine of y, so those are not like terms because the variables switch places. But sine of x cosine of y and sine of x cosine of y, those two can go together. So we actually have two of those. And then here we have cosine of x sine of y minus cosine of x sine of y. So these two terms are similar, except for they're going to cancel out. So now we have 2 sine of x cosine of y equals 2 sine of x cosine of y. We finished it in just basically 2 steps. And when I first looked at this proof, I saw 2 sine of x cosine of y, and I thought, well, isn't that just sine of 2x? It looks very similar, but the reason we can't say this is because this cosine of y, since the variable changes, we can't just combine this all into one trig term. But that's besides the point, because that's not what we're trying to prove anyways. All right, for number 17, we have cosecant of 2 theta equals cosecant of theta over 2 cosine of theta. The right side looks a little more complex just because we have a fraction, but since we have this 2 theta over here, and we've learned some double angle formulas, I'm actually going to choose to work on the left side. Unfortunately, we don't have a double angle formula for cosecant of 2 theta. So I actually have to use like a reciprocal identity first and think of this as 1 over sine of 2 theta. And now we do have a double angle formula for that. So I'll leave this as 1 over, and then sine of 2 theta would be 2 sine of theta cosine of theta. Now we're really close. We have the cosine and the 2 in the denominator that we want, but we have the sine in the denominator, and somehow we want to have a cosecant in the numerator. Well, of course, sine and cosecant are reciprocals of each other. So you could say instead of dividing by sine, let's multiply by its reciprocal. So I'll put cosecant of theta on top, and then we just have 2 times the cosine of theta on bottom. Example 18 will be the last one for this video, and it says sine of 4th to the x equals 1/8 cosine of 4x minus 1/2 cosine of 2x plus 3/8. Now the right side obviously looks more complicated. And honestly, we have 4x and 2x. We have 2 different types of angles going on, basically. So it might seem natural to work on the right side, but the fact that we have so many different things going on makes it kind of complicated to do anything over there. Like, these are not like terms that we could put together. And also we have cosine of 2x, which we have a formula for, but then we have cosine of 4x, which you'd almost have to think of as cosine of 2 times 2x. So then this would be like doubling the angle of 2x. So it just gets a little bit complicated working on the right side. So I'm going to choose to work on the left side, and let's just see what we can do. The other thing is we have these power reducing formulas. So we saw that sine squared is 1 minus cosine of 2 theta over 2. And that seems like it might help me because over here we have sine raised to some power, and it changes it into something with a cosine in it, which is good because we have a bunch of cosines over here. And it changes the angle theta into something like 2 theta. But we don't have sine squared, we have sine to the 4th. So I have to think of this first as sine squared times sine squared. And now I can start changing these using this formula. So now we have these 2 fractions. Let's see what happens when we multiply them together. So on top, I basically have to FOIL 1 minus cosine of 2 theta times 1 minus cosine of 2 theta. So 1, and then we'd have minus 2 of these cosine of 2 thetas. And then we would have to multiply these together. So negative cosine times negative cosine would be positive cosine squared of 2 theta. All of that over the denominators multiplied together, which makes 4. Now let's just hit pause for a second and see how much closer we are. It doesn't really seem like we got any closer because now we just have this big fraction to work with. But if you were to like separate this out, like just look at this middle term. We've got minus 2 cosine of 2 theta over 4. And the 2 over 4 will simplify to be 1/2. So we actually have this middle term already. So just to keep things organized, I'm just going to pull that out front first. So this would be like minus 1/2 cosine of 2 theta. And then let's see what else we have. We had 1 plus cosine squared of 2 theta, all of that over 4. So now we just have to work with the rest of this fraction and somehow change it into the rest of this stuff. So since we have cosine squared, I'm going to use the power reducing formula for that as well. And cosine squared of theta equals 1 plus cosine of 2 theta over 2. Now we don't have an angle of theta inside, we have an angle of 2 theta. So since this angle gets doubled using this formula, we have to do the same thing here. So this 2 theta is going to change into 4 theta. So it's going to get kind of messy because we'll have a fraction inside a fraction, but I'm going to write 1 plus cosine of 4 theta over 2, and then all of this is over 4. So now we just have to work on simplifying this down. So the first thing I'll do is split this up, this numerator, because we have 1 over 4, so I'll just write that as 1/4, so plus 1/4, and then all of this stuff. So think of this fraction as being over 2 and then being divided by 4. So if you divide it by 2 and then divide it by 4, that's like dividing it by 8. So we'd have 1 plus cosine of 4 theta, and that would be over 8. So now we have one more fraction, and I can split this up too. We've got 1/8, and if you add 1/8 and 1/4, that's how you'll get these 3/8. So I'm just going to kind of check this off for a second. This was the middle term. The 1/4 and 1/8 will go together to make 3/8, so that's good. And then we'd have cosine to the 4th over 8, and that's the same thing as 1/8 of cosine to the 4th. And I just realized that I switched all the x's to thetas through almost this whole problem, but oh well, it's not a big deal. So I kind of ran out of room here, but your final step would be to write out both sides. And that's the last of the 18 examples on proving trig equations.